Our next speaker is Enrico Olivucci, who will speak about Toda BOOTSTRAP, null-polygons.
Okay, so good afternoon to everybody, and I'm really glad to be here, back in person in IGST. I want to thank a lot the organizers for inviting me to give a talk in here. So today, in fact, I will speak about some results related to higher point correlators in gauge conformal field theory. The plan of my talk will be structured as follows. So I will give an introduction with some motivations, and I will point out which objects do we deal with. Then I will explain in which particular kinematic conditions do we work and what effect we expect and in fact observe about higher point correlators. And finally, I will explain our result. What is our result, which is a conjecture for some objects I will call null polygons. Finally, if there is some time left over, I will put a timer, in fact, I will be able to provide you some not so technical detail and answer or formulate myself, in fact, some questions. So we deal with the N=4 theory, which is conformal gauge supersymmetric field theory, and we will restrict ourselves in this work in the large N-limit, therefore with planar correlators. In fact, we not only consider planar correlators, but planar correlators of very simple operators, which are, here there is a square missing, of course, second power, which are operator of, I'll consider them to be operator of two scalar fields. You know very well N=4 has 6 scalar fields which are distinguished by an index I, and those fields are contracted with a null tensor, a null vector y, which means such an operator will be a symmetric traceless tensor. Okay, but this property of being a symmetric traceless tensor with respect to the R symmetry SO6 or SU4 if you prefer, is such that due to supersymmetry, this operator do not get corrections to their scaling dimension. And therefore, say the object of our general research is to study endpoint functions, that is, in the planar limit insertion, if you want, on a sphere of n BPS, 1/2 BPS operators, each standing at a certain position in the space-time X, and being characterized by a certain polarization vector Y, which determines which component in this 6-fold vector are selected. Okay? In fact, these 1/2 BPS operators are very simple, not only because they are protected in the scaling dimension, but also in the 3-point function. Nevertheless, their 4-point function is not trivial. Okay? And it is a very interesting object for the following reason. Because we have OPE. Therefore, we can use a 4-point function of operator which are very boring in a sense to extract information, very non-trivial informations about operators which have correction in the scaling dimension and are even spinning. Simply, if I consider the operator product expansion, when the position of the operator O1 gets closer to that of the operator of 4, and similarly, or equivalently, I should say, 2 and 3, well, we know that I can expand this 4-point function in a certain function fixed by symmetry, the conformal block, and which are multiplied by certain 3-point structure constants, which are the 3-point structure constant of the 2 external operator and a certain primary operator of dimension delta and spin S. Okay? So 4-point functions are, in a sense, a tool to extract information about 3-point functions. Okay? So in fact, if we stick to 1/2 BPS operator, we can still study not only structure constants of 2 BPS operators and a non-protected spinning operator, but we can do better, right? Because if you consider higher point function, and that's why higher point function, in my point of view, in our point of view, are a very interesting problem to study, despite the fact that in a conformal field theory, 2 and 3 point function, in a sense, capture the content of the theory, is that because they are sources, they are, if you want, machines that produce a lot of non-trivial conformal data. And you can think about this along the lines of the work of multiple groups that I reported here, and I'm sorry if I'm forgetting anybody. So you can take, for example, multiple OPEs, such that in the operator product expansion that produces that is expressed via a sum over non-protected and spinning primaries. So these spinning and non-protected primaries, they can OPEd, they can put close to other operators, be they external or being then the result of another OPE, and getting in this way structure constant, therefore 3 point function in the theory that involve less trivial operator, a more complicated operator rather than 1/2 VPS. Okay? This is the pictorial example I'm giving is a particular channel, so a particular way of taking these limits, but it's not the only one. And in fact, not being the only one, it allows to do some bootstrap. Okay? So now I want to, after giving this motivation, which is, I think, a very good motivation to learn something about higher point correlators in the theory, I want to show what is the type of object we deal with and in which situation can they appear. And those objects are the disk correlators. Right, so if I consider a planar theory, generally speaking, I will be able to see that all the Feynman integrals entering the perturbative expansion of the correlator can be drawn, in fact, on a sphere, okay, on a surface of gene 0. But there are certain limits, certain conditions under which the sphere is factorized into the product of 2 disks. And these are the kind of correlator I want, the kind of situation I want to study. So if I consider just a 4 point function so far, and I consider 3-level graphs that describes this 4 point function on the sphere, well, you can see that these are given by product of propagators that here I draw using these black lines connecting red dots. And if the correlator is planar, you see there are only two possible choices for the most general skeleton three-level diagram, which are what I'm drawing here. There is nothing more. If I want to have something more complicated, I must, if I don't want to cross the lines, add genus to the surface, right? So go to non-planar suppressed corrections. Okay. Now, so here I'm just reporting the notation I'm using. And so in fact, the general three-level scalar, the general three-level skeleton diagram is, after all, characterized by the number of propagators that extend between each couple of points. And the propagator stripped of constants is basically this type of object. I'm considering scalar fields. This is bare propagator. I have a numerator given by the scalar product of these polarization vectors and a certain denominator. Okay? So in perturbation theory, in order to understand now under which condition this sphere factorizes into 2 disks, you can consider perturbation theory and see how to perform the perturbation theory of a certain skeleton diagram, so of a certain contribution in the correlator. Well, as usual, just if you want by Lagrangian insertion method, or simply, every time I add a certain power of the coupling, I will also add a certain, add one vertex. Okay, one interaction vertex inside the graph that will contract with the fields and will be integrated, and so on and so forth. So, in fact, from this point of view, you can distinguish clearly 2 situations. If I consider, again, 4 points, here I'm explicitly drawing more propagators. Okay, so for example, this hashtag here will be 3, or on the other side will be 3 as well, but it's very generic illustrative picture. The difference between what I have on the left and what I have on the right is that what is on the left are vertices that are inside the square, while they could be outside the square, right? Because I am on the sphere. Everything which is outside of the square is on a disk. Everything which is inside the square is on another disk, and the two disks are glued along the square contour. While what is on the right, you see it couples the inside and the outside of the square, because you have some vertices which pass across this bundle of propagators in the square frame. Okay? So it is clear that this type of contribution, this type of correction in the perturbative expansion can happen only at a certain, they can start only at a certain loop order, right? Because they should traverse all these propagators. So there is a minimal number of vertices that you need in order to have such terms. And the idea that was used, for example, by Frank Coronado in his study of the octagon was to push this number of propagators along the bundle to infinity, and in this way somehow to decouple the inside and the outside of the sphere into two disks. This is in fact very inspiring for our work, and in the end I will show this concept will come back, or rather I should say this framework will come back in our investigation, but it is not what we did. Okay? So the general picture, this general picture I'm proposing can be achieved actually not in this, not acting on the large charge or the large dimension of these 1/2 BPS operators, but rather using a particular kinematical setup. Okay? So what I want to achieve is in general, right, this factorization of a certain sphere with the various correction into the product of two objects which are in a sense independent, so they are completely factorized, and you can see the inside of the disk being the first object, the outside of the disk being exactly the second object, okay? With its perturbative correction, which can happen only inside or outside of the square contour. Okay. And this other framework in which this decouple happening is a specific double scaling light cone limit for the propagator, for the correlator, sorry. Once again, here I'm still restricted to 4-point functions, but I later generalize this to higher points. So what does it mean? I want to consider 4 points, these 4 points that are connected by propagators, to lie on a null contour. So every edge of this square to be in fact null. And we know that besides, of course, the power law divergence that stands in front of the correlator, so the leading, this leading singularity, then there are also, in presence of quantum correction, logarithmic divergences on the top of that, because, well, you know from the structure of the conformal block in an OPE, for example, that there is a part containing log z bar. And if I consider 3 points on a line, which I can always do in a conformal theory, 0, 1, infinity, and the third point, here should be z and z bar, somehow the bar was cut, I'm sorry, but this 4 point is on the plane. If I consider the OPE, which I presented before, okay, the conformal block as I can factor out the singular part of the conformal block when z goes to 0. Okay? Setting z to 0 means setting these two distances, which are dashed, to be null, to be on the light cone, and therefore producing log divergences from this exponent. Okay? But taking this limit, which gives indeed infinite quantity, forced to restrict to some finite quantity, which we define via double scaling, which extract the so-called leading logarithm, so the leading logarithmic divergences. Sending the coupling G to 0 and the edges to be null, but setting G square log Z to be finite, well, one discovers that the only corrections, the only coupling-dependent corrections to this 4-point function are in fact encoded in the one-loop anomalous dimension coming from this exponent in the conformal block expansion. Okay? While this second function is regular when z goes to 0. Okay? Then we want to do more because we want all the contour, as I was mentioning, all the square to be made of null edges. So a second limit can be taken, that is z bar going to infinity. When z bar going to infinity, well, also this function f will contribute with some divergence. And in fact, the real double scaling limit we will consider is not just g square log z, which would be the leading logs in the light cone OPE, but it is g square log z bar to be finite. Okay, and so we can define a variable s. Here I report s to the 2n, and it is an observation that at n loops, that is at order g to the 2n, you can have maximally log n to the z and log n to the z bar. Okay, and so this is the new variable. So if you can compute a 4-point function of 1 BPS operators in this double scaling limit at every value, at every loop, at every power of g, but in this double scaling limit, which means at every power of s, then you have a no loop result, which from the point of view of the dynamic of the quantum corrections to the 2-point functions depends only on the one loop dilation operator of the exchanged operator, right? Because it depends only on gamma 1. And this is the limit we are interested in. This result is known. This result is known, and I invite you to consider this picture of the skeleton diagram and imagine that this is not just this 3-level diagram, but you can consider all the corrections that you would get in the perturbative expansion. And therefore, in the double scaling limit, you get a function of this variable s I just defined. And this object indeed shows this factorization that it is expected into 2 functions, depending, as you can see, only on the number of propagators connecting point 1 and 3, the first function, O with L, and the number n of propagators connecting 2 and 4, the second function, O n. So these are exactly the same class of functions, but they are distinguished by these indices L and n. Okay? This is pretty remarkable. It does not depend on how many propagators connect 1 with 2, 2 with 3, and so on. So it does not depend on which 1/2 BPS operator we are considering, how heavy those objects are. Okay? You can consider, of course, 20 prime, for example. Well, in that case, you will not have enough propagators to have any L or any N, but you can consider 3, 4, 6 length operator, and the story will be the same. Right? So this object is computed, in fact, and this computation is based, in a sense, of on some integrability technique, which I cannot explain here, but take it as a known result and observe it that it is given by a part which you could call Sudakov factory if you want, but it is this exponential of minus s squared, okay? And then another function which depends on how many of these propagators, diagonal, non-light-like propagators are in the corresponding skeleton diagram, and this function is in fact also known at exactly. In fact, it is a solution of a well-known integrable hierarchy, the so-called Toda equation. This Toda equation, in fact, can be solved non-perturbatively exactly, and it takes the form of a determinant of modified Bessel function. So you have a matrix of size n, where n is the number of this diagonal propagator, which from now on I will call bridges. And it is an n times m determinant of modified Bessel functions. But in fact, even if you didn't know the integrability story that gives you this determinant, you can still observe that the equation is homogeneous on the left. It is not the case on the right. And so given some initial boundary condition, you can solve iteratively this equation to the order you want. Now, in fact, this result I presented so far is not our result. It's a result by Andrei Belitski and Grisha Korchemsky. Therefore, what we want to do is consider higher point functions. And a suggestion in this sense comes from the fact that, from an observation that if you take 1/2 VPS, or maybe I should say short, or not only 1/2 VPS in fact originally, but let's say short operators like 20 prime operators, if we look at 1/2 VPS, but also Konishi. Okay, yeah, if you take endpoint function of say 20 prime operators, and you consider this limit IM focused, edges along the polygonal contour to become light-like, there is a correspondence between the correlator, so the correlation function, and Wilson loop in the n equal to 4 theory. Wilson loop on the polygonal null contour. Okay, and this correspondence was pointed out in the literature, and it was also by Aldai, Korchemsky, Eden, Maldacena, Sakachev, but it was also used much more recently in order to bootstrap, in some bootstrap paper about correlators of 20 prime operators, of 5 or 6 20 prime operators, where you can really see in practice how the result contains the information about, is based on the information of the Wilson loop. Well, this correspondence is suggestive because the Wilson loop in this limit enjoys this factorization, where the adjoint Wilson loop gets factorized in the product of two fundamentals, and therefore makes us think that this factorization of a sphere into disks should hold also for higher point function, and not only for 20 prime operators, but also for any 1/2 VPS operator. Therefore, also in that situation where you have these bridges, where you have not only a contour in the skeleton tree-level diagram, but also some diagonal propagators, which will give a very non-trivial and interesting structure. So let's focus on this type of object, and these are what we worked on. And consider 20 prime correlators in double scaling limit of n 20 prime operators. One know from this correspondence, taking the double scaling limit I have described, that this propagator has precisely this form. Okay? So it's the exponential of minus t1 square, minus t2 square, minus tn square, where ti is a kind of cusp variable, so there is one variable for each cusp of these polygons, that is for any 1/2 VPS operator, defined according to this double scaling limit. Okay? So g squared times the logarithm of the distance to the left of the point I times the logarithm of the distance to the right of the point I. This comes from the correspondence, but we want to consider indeed more involved situation. Okay? In a sense, if you consider the same prescription on 4 points, you would have only e to the minus s squared. We want to understand what would replace for a higher point this solution of the Toda equation, this nice determinant. Okay? Okay, this is really the same. So what about the pentagons? Okay? Now consider a 5-point function and consider a tree-level diagram. Okay? Tree-level diagram, the most general tree-level diagram you can consider without crossing lines, so in order to be planar, is the following. Okay? So you have 2 points that can emit 2 propagators that don't stay on the light cone contour, one inside emitting h and k, and one outside emitting h prime and k prime propagators. It's obvious that you cannot have no other tree-level contribution is possible if you want to be in the planar limit, right? This is the most non-trivial, the richer one. Okay? And so the claim, the conjecture, our conjecture is that if you consider this object and you send indeed this light blue contour to be on the light cone, this contribution, and with all its perturbative corrections, factorizes into 2 functions, which I will call P here as pentagon. Each function depends only on h and k and h prime and k prime respectively, so only on the number of propagator of the original skeleton, of the original tree-level contribution, and is completely insensitive respect to the other. Therefore, inside and outside of the pentagon, the couple, the two disks, the couple. And those are functions of these double scaled t variables, each for every cusp. Okay, this is a conjecture, but what are these functions? Okay. We know what are these functions. We can conjecture also what really these functions are. Okay, so once again, I have this exponential factor, which one could guess from the knowledge of Wilson loop and the correspondence with the 20 primes. But in presence of non-zero h and k, I will have also a non-trivial function phk. And what we find perturbatively, and therefore we do conjecture non-perturbatively, is that this function p also solves a system of Toda equations, but actually a system of two Toda equations, which are more complicated each respect to what is in the case of the square, because are two-dimensional Toda equation, or even called Toda field theory. And maybe you don't recognize them. If you don't recognize them at a glance, is because you can do a change of variable and set them in a more familiar form that you have for the position of sites in a Toda lattice. Okay, these functions have two indices, h and k. Therefore, each, I want to explain somehow graphically how do you read these two equations if you look at the null pentagon I draw on the right. Okay, so you have one first equation. Okay, you see it contains only three variables, t in the differential part, which are 1, 2, and 5. One has a special role because it's not extreme of this bridge, of this black bridge. And this, as a Toda equation, it acts only on the first index. You see kappa, index k is always the same, while index h is shifted. And similarly, the second equation deals with the second index k and deals with the second set of three variables. Okay? So this is how you read equations if you look at this pentagon. Now, once again, these two equations are homogeneous on one side, non-homogeneous on the other side. Therefore, if I supply with certain boundary condition the system of two equations, I can solve them at all loops. And in fact, you can guess and check after you develop some experience, of course, it's a matter of guessing, that when you send these two special variables 1 and 3 that play this, that I depicted with the hat, that play this special role in the two equations, because they appear on the right-hand side, if you set them to 0, this object factorizes, and it factorizes in this tau function that appeared as a non-trivial part in the square case. Okay? This tau function, one tau function each for each non-zero cusp, okay? So 2, 4, and 5, and with index the sum, so the total number of propagators emitted by that cusp. Okay? So th plus kappa from 2, th from 5, and t kappa from 4. So now you're ready, after knowing this case, you are ready to guess what is the story for higher polygons that there is for hexagons. So consider a 6-point function, focus on a certain contraction in 3 level, and consider its the perturbative correction to it in this double-scaled null contour limit. So here, it is very instructive. I'm not listing hexagons because I could go on forever and I want to occupy time. It is just because it's the first time you get more than one possibility how to dispose the bridges. So these lines, these black lines inside the polygon. Before, they could be only at most in these two directions. Okay? They could be at most 2 and for sure both emitted by the same point. Okay? While here there are 3 possible topologies. Okay? So we distinguish these A and B and C situations, And you can, of course, assume the same conjecture, so having the exponential part, Sudakov term, times a non-trivial function of these t variables. Now, how to fix this non-trivial part? So what are, in this case, the differential equations, and how to guess or to compute the boundary conditions? Well, let's look at this picture. So we recognize, for example, in picture A, twice the same situation it was in the pentagon. So twice bridges, which I depict with blue, that connect next to neighboring points. So for which there is a kind of spectator point, which I depict with a hat. So 1, 2, 6, and 2, 3, 4. And similar in situation B, but differently in situation C, I have 3 of these triangles. Now, in the case of the pentagon, each triangle was associated to a Toda equation, and therefore I can assume the same logic. Okay? So I will have, in the first, for this situation, for this A configuration, there will be 2 Toda equations, but there will be two Toda equations that share one point at the level of the differential operator. So in both differential operators of this Toda, there will appear the variable T2. In the second situation, B, this is not the case. There will be 2 decoupled Toda equations. Okay? And in the third situation, there will be 3 coupled Toda equations, as you can read just from the picture. Okay? And in fact, what will be the boundary condition now in order to fix the solution of the system of Todas? And in particular, this tells you where do M, these red bridges of index M, enter in case A and B, because they don't contribute to Todas, right? Only bridge L and N are shifted by the corresponding Toda equation. Right? Let me make this point clear. Going back to the previous picture, I would like this point to be clear. You see, if my triangle, which is associated to a Toda, has this basis with index H, you see that only H is shifted in the 2D Toda equation. Okay? So similarly, the Toda equations in case A and B shift only L and N, and L and N respectively. Okay? But M, therefore, in this case, will just play some role at the level of the boundary conditions, because I use the same prescription for boundary condition as explained before. So when I set those particular hatted point to have a corresponding t variable to be 0, the result factorizes into tau functions, and this tau function have index, so functions in the 1D Toda hierarchy, with index given by the total number of propagators, bridge propagator emitted by them. Okay. So here, of course, now M enters, and it determines the solution. Of course, the type of system of Toda that you would get, coupled, uncoupled, will then eventually show up at the level of the solution in terms of eventual factorization of different part of the polygon, further factorization. But that depends totally on the configuration, right? For example, in case C, all the Todas are coupled, so there cannot be factorization. In case B, you see that the left and the right part of the hexagon somehow they don't speak to each other, okay? Because there is no equation to couple them, so they will be actually factorized. Okay, so the general conjecture you can do for an n-point 1/2 VPS correlator, if you focus on a certain skeleton, and let me tell you, you can choose at least to 5 points for certain the polarization, the y vector, the polarization vector of your BPS operator. So the precise choice of the BPS operator such that there is only one simple class of these skeletons. So for each of these skeletons, you can, in the null contour limit, assume factorization into 2 polygons, into therefore n-gons in general, which are labeled by the number of bridges, so these propagators that do not lie in light cone direction, and depend on the t variables, 1 for each vertex of the polygon. And we can conjecture at every loop what these objects are, therefore the Sudakov term time a solution of a system of Toda equations. Okay? Once again, you will draw your polygon, you will draw the bridges, and you will observe how many blue triangles there were, and so how many Toda equations, and how many vertices the polygon have, and you will be able to read for every vertex what is its contribution to the boundary condition depending on how many bridges it emits. Due to the fact that these Todas are not homogeneous left and right, you can iteratively solve to any loop and find the solution for the object I started from, that is the endpoint function. Okay? So I would ask how much time is left over?
You started a bit later, so I think you can 37. You have 7 minutes more.
Perfect. Okay, since I have 7 minutes more, I think it is a good idea. It is a good idea to explain you what does it mean that we have conjecture, because so far I tell you that we conjecture stuff, but the conjecture is based on perturbative computation, which goes up to 5 loops, or 4 loops in the 5 loops for 5-point function and 4 loops for 6-point functions. Okay. So perturbative data. How do we produce perturbative data? Which we look, and with some intuition, we use to guess this system of Toda equation and boundary condition. Well, let's consider the 5-point case. Okay, I have 5-point case. I make a particular choice for the name of the position of the 5 operators, and this is totally generic, because I can reach this configuration by conformal transformation. I have 4 points that lie on the plane, ZZ bar, WW bar, infinity 0, and then I have a 5th point that I cannot put on the plane by conformal transformation, which is 1, 1 plus a contribution outside of the plane. This vector E3 is just in the 3rd direction, and I will label by square root of 1 minus V. It's not so important at this level, but it is a convenient choice. So then, how does it work, our algorithm, to produce the data? First, we always choose 2 edges to send to null direction. For example, setting Z bar to 0 and W bar to infinity. It's clear that since you will recognize I'm writing points on the plane using light cone coordinates. Therefore, when Z bar goes to 0 and W bar goes to infinity, these 2 light blue edges are indeed in null in light cone direction. Secondly, I consider the simple Taylor expansion of these 2 edges of one extreme, that is of the field that lie on one extreme, around the other. Okay? And let me point out that, as you see, I'm considering only the inside part of a 3-level diagram, right? I'm already considering only what I will call then null polygon. Everything which is outside is already factored out. So also the SUN index structure of the fields that appear will be open. Okay? So yes, I'm just doing a Taylor expansion, you see. I have a sum in Z to the J and in W to the J prime, 1 over W to the J prime, because I'm expanding around infinity, of what? Of a 3-point, now this is a 3-point object, because this point is 0, these points are in 0, these points are in infinity, there is insertion of some derivatives over certain points, okay, because I'm expanding, of course, and then there is a 3rd point, which is always this 3rd one. Now, at this point, what are the objects sitting in 0 and infinity and in the 3rd point? Well, there are fields. So there will be here. Let me consider, for example, that the thickness of these 2 blue bridges is just 1. Okay, and similarly for the thickness of the other black propagators. But this is really the thickness of the black propagator can be whatever bigger than 1. Okay, it's not important in the null limit. So you can easily identify now what are these states in spin chain language. You can identify these points, 0 and infinity, and the 3rd point with spin chain states. Okay? So I have a first field on which I act with a certain number of derivatives due to the Taylor expansion, then the 2 blue fields, and finally the 4th field. Okay? Similar in infinity, I have a first black field that connects to 0, then the 2 blue fields, but the second blue field and the last black one are, of course, acted on by derivative due to the Taylor expansion once again. And then I have one emitted and absorbed field, if you want. Okay, so I have two fields here, which should contract. Okay, then these states, these bra and cats of a spin chain should contract. Now, these states are open states. They don't have cyclic boundary condition because I am factorizing the sphere into two disks. Okay? Right, so now I hope the colors are visible. You see this yellow contracts with yellow, blue contracts with blue, and brown contracts with brown. Okay. So the open spin chain states where excitations are derivatives. So I can already tell you that, and this is an observation in fact, is if you want, not that trivial, that in the computation in this double scaling limit, it's not important what is the SU4 index of this field. Right? The only thing which matters is that there are scalar fields, and what matters is the number of derivatives acting on them. Okay? So you don't really need to distinguish. Excitations are purely given by derivatives. Okay? And in fact, what are the quantum corrections now to these objects? Well, what would you do when you? It's similar to what you would do in a normal, in a usual OP, right? You put close to each other two operator, and you exchange a set of primaries that carry a contribution of the type e to the minus log of z, or log z bar, times the scaling dimension. So similarly here, on the state in 0 will evolve under the action of the dilation operator, which is the one loop dilation operator, as I explained, which is the only quantum correction part important in the Lightcon double scaling limit. So e to the minus log z bar to g square, one loop dilation operator, and similarly e to the log w bar g square to d. Okay? Because w bar, which captures the dependence in w bar and z bar once we set these two edges to be null. Okay? So the only computation we have to do is to take this bottom state, which is the state at infinity, evolve it in applying the one loop dilation operator in the exponent, similarly taking the top state with insertion of derivative j prime, which is the state in 0, evolve it with again one loop dilation operator, and then contract them among each other and with the state, with this third state, which is more formally written here in the middle, and compute what is the number. So yeah, we really get tables of numbers when we study different value of changing the values of j and j prime. Okay? This number is what we call stampede, because in a sense is the movement of derivatives which are on a first side here in 0, that they should move on far, they should run away, in a sense, far away from this first side, because you see in infinity there is no derivative, so if you would have derivative in 0 but not at infinity, this would give you 0 because of simple scalar product rules. So somehow they are running away like in a stampede. Okay, knowing these numbers, knowing this stampede, you can then resum your Taylor expansion of the two null edges and get a function that loop by loop will be a function characterized by certain prefactor as power of log. There is, of course, a stratification in logs, and which multiplies a function of the other cross ratios. Okay? So we have 5-point function, therefore 5 independent cross ratios, z bar, w bar, and this fifth v variable. And this function is what you really obtain out of the resummation. Okay? Now the point is, how do we recognize out of a table of numbers that we can compute with Mathematica what these functions are? Well, we use, and I'm really grateful for this with the previous speakers, we use symbols, because thanks to the fact that the one loop dilation operator effectively acts only in its SL2 component, so it doesn't distinguish different SU4 indices, the result, this function f that appear loop by loop with a certain stratification of logs, are always purely transcendental function. There is no rational part to guess. This is an effect of having SL2 only in this limit. Okay? Otherwise, you would have indeed some non-trivial rational prefactor related to leading singularities of the various Feynman integrals appearing in the perturbative expansion. Okay? So long story short, you get at every loop order, say g to the 2m plus n, a certain term in log m log n, times a certain function, and you here recognize that the arising of the variables t that I introduced in the beginning. So g squared log, in fact, is, if you notice that log of z bar, log of w bar is distance, is log of the distance on this first edge and this second edge, these are variables of the type log, g squared log of x squared of a certain distance, log of x squared of another distance. So finally, this is how we produce data. The various data for the various possibility, given the various number of bridges, okay, in this pentagon, starting from a very simple iterative application of one loop SL2 dilation operator. Okay? So then we have the data and we work on this and we guess and we check Toda equations. Okay. So let me conclude. What are the next steps of our research now that we believe that we know very well this null limit? Well, it's going to more general kinematics, but still staying in this simplified regime where the sphere factorizes into two disks. That means that we can mix the condition which allows us to cut a closed contour and factorize indeed the sphere into two disks by mixing edges which are null, for example, and edges which are connected by a very large number of propagators. Okay? So mixing the two conditions of large charge used in Franck's octagon and the null distance that we use in this work. In general, we expect then this object to be, of course, richer in terms of kinematics, and to be described still by a certain expansion in leading logs, but to fully capture, and not only leading logs, the dependence on the three other cross ratios. In this sense, it would be also easier, very nice to understand, not easy, absolutely, but very nice to understand what is the relation, as we have a relation between 20 prime and null polygonal Wilson loop. What is the case of this relation, if there is such a relation? When we don't have 20 prime, we have longer operators, so we have non-zero bridges, which is those functions that solve Toda equation. What does it mean in terms of Wilson loop? Is there still a correspondence on the Wilson loop side in that case? There are nice determinants. After all, this Toda equation takes the form of determinant. And the determinant appears also in localization for Wilson loop. So it could be a coincidence, but maybe not. And also, could we derive directly these null polygons, not from our algorithm, but from integrability, from hexagonal formalism computations? And is this result valid as it was suggested to us by Grisha Korchemsky? In general, quantum field theory with 0 one loop beta function, for example, even in QCD, when you set number of colors and flavors such to make 0, one loop beta function coefficient, and one loop because the dynamic is one loop, as I explained before, for these leading logs. Or even more, we can think about subleading logs, noticing that in the square case, we derived a Toda equation, even for when we include first subleading logs with Pedro, or even for finite number of colors in the theory, as was actually suggested by Thiel. It would be interesting to see if this factorization still goes on. And maybe I should add, for example, a question by myself to Eduardo. What about determinant operator? Okay. So could you think about something, some factorization, even if you have instead of trace, single trace operator, single determinant, one of BPS operators in the theory? Okay. Thank you very much. I hope it's correct. It's Google Translate.
Question?
You mentioned that you get these Toda equations in the coming from Toda field theory. Could you imagine some way where you would quantize and you would get, instead of derivative, you would get a finite shift, so similar to Hirota equations for characters and so on?
So we have finite shift, right? But
I
you
mean,
want
in the
to have-
left-hand side, you have derivative in your parameter.
Yes, in the left-hand side. That's right. The short question is no, because that would mean to discretize this cusp variable. I don't know what it would mean.
So this determinant is very similar to the expression we found with Amit for the two-point function in near BPS. If you like replace it on some angles in the Wilson cusp by your S, I guess you can match it exactly. So is there any reason why, and it's also obviously something which Schroter can connect with localization. So is there any reason why it's like that? Can you see any link?
So this is a very good point. Actually, many people always point this out, because also from localization there is really, indeed, as you say, there is right, some twist, some angle, but after all it's a determinant of modified Bessel functions. Well, the origin of this localization result and of our result seems very different, because we reach it in this very particular kinematic. So in fact we do not know. But due to the correspondence between null polygonal Wilson loop and correlators in this null limit, I think it is a very interesting direction to explore. Maybe not starting directly from the localization point of view.
Following up Cole's comment, I suspect it's related to the following fact. So if you consider very large spin operators, then it's often easier to consider it by mapping it to ADS3 times S1. And once we map it to ADS3 times S1, at weak coupling, you can integrate out KKMOs and then reduce it to the 2D mills with some higher derivative corrections. And in 2D mills, often you get a really expression similar to that. So I suspect it might be coming from the fact that both localization and this large spin limit, or a null limit, are related to the 2D mills.
Hi, very nice talk. I was wondering, is it possible to play a similar game in a three-dimensional theory like ABGM, for which we don't know, so much yet?
ABGM?
Yeah, can you play a similar game and get
Yes.
maybe some determinant prediction for some correlation function in ABGM?
So it is definitely possible to play this game. Now, the main difference, it is not in how to produce perturbative data. We can produce perturbative data, assume that our stampede algorithm can be applied in the same way, and in fact we did and already tested on some known cases, for example, the 4-point function of 20 prime. But the problem is on the ANSATZ. Okay? So in n equals to 4, we know that at n loops, here we would need an ANSATZ that in terms of symbols, even without symbols, these are uniformly transcendental function of n letters in the symbols of length n. Okay? And these are what? Multiple polylogarithms of Goncharov polylogarithms which have been explained in the previous talks. Now, in ABGM, this is not the case. Functions that you observe appearing are more complicated. Okay? And in fact, now I'm stimulated by this morning talks. Maybe one should look at the basis of elliptic polylogarithms or stuff like that. But even more, there is another point which we couldn't clarify far when we compare our knowledge from the perturbative data spin chain method and spin chain method wise and Feynman diagram wise. Okay. So in n equals to 4, for example, we know that all the functions will enter here will be ladders or determinant of ladders, in fact. In ABJM, you can try to reproduce the same logic and start to compute this analog 4-point, for example, 4-point conformal integrals, and compute them at least in the Lightcon limit, because we need only their leading log. But in fact, what you would immediately guess it enters is not enough to explain. It's not enough to explain the result that one gets both from the OP and from the perturbative data, which match with themselves. So, yeah, we don't know yet. We don't have our feet on firm ground yet. But I don't see any reason why it shouldn't.
No more questions. So I would like to ask something related to your last transparency. So the last one. So you mentioned total field theory, yes, which appears in the general lights like polygon, yes.
Yeah.
So maybe this is related to, I mean, if you have just a square, 4 points, then does it mean that you have also total field theory
no.
equation?
In that case, you have the Toda equation due to the fact that 4 points is a simple situation where you have only z and z bar, you have only 2 cross ratio, and therefore in the double scaling limit you have only 1 variable. Okay, so for 5 points you have 5 variables, t1, t2, yes. T5. For 6 points you have, and so on. But for 4 points you have only 1 variable. And in that case you have therefore not field theory. You have only time variable, not space variable.
Well, but you have z and z bar. And you can take one variable, which is the logarithm of z divided by z bar, and the second variable, which is the logarithm of z times z bar. So you have 2 variables, and actually you have a total field theory equation which depends on these 2 variables.
Yes. It's true. That's true, that's true. This is why I'm referring here to these subleading logs. In this, we also observed this in this work, just for the first subleading logs, that in fact you can, in our work we called LL bar, the S variable, and L over R bar, somehow this correction. And it is it becomes field theory. And in this, following these lines, therefore, we hope and so far believe, but one has just to compute, that maybe our equations that are valid as total field theory for higher polygons, maybe they just remain untouched when we go to subleading logs for higher polygons, and the only difference at that point arises only from an improvement in the boundary conditions that will take into account subleading logs.
I see. Oh, thanks. Okay, thank you, Enrico, for the very nice talk.
Thank you very much.
So we have a 15 minutes break before the last talk of this afternoon.